Good afternoon. Okay, absolutely fine.
Good afternoon, everyone.
Good afternoon, Shalini.
Yes, ma'am. Shall we start? Ashish sir has joined, I guess.
Yes, if Sir has joined, we can start. It's already
Oh,
3.
okay, ma'am. Okay. So, good afternoon, everyone. Now we have today's second session on wind energy conversion, system, current trends, and challenges. So, today we have Dr. Ashish Srivastava sir with us. So, he is currently working as Dean SFET Skill Professor, Electrical Engineering, Dean NAC, IQAC, under Department of Skill Faculty of Engineering and Technology at SVSU, Haryana. Dr. Ashish sir earned his BTech and MTech degrees with honors in electrical engineering from Government Engineering College, Rewa, MP, and MA NIT, Bhopal. He is awarded PhD on power quality improvements in lighting systems from the Department of Electrical Engineering, IT Delhi. He has been conferred with prestigious POSCO Power System Award 2014 under the doctoral category for his outstanding research work focusing on low-cost energy-efficient electronic blast LED driver for low-power lighting applications with power factor correction. He has a rich experience of 22 years in academics and has published more than 90 research papers in peer-reviewed and indexed international journals of his repute, including IEEE transactions in industrial electronics and IEEE transactions in industrial informatics, etc. With a flair for research and hands-on approach, he acquired expertise in design and implementation of DC-DC converters for power factor correction in many applications, such as different lighting loads, SMPS power supply, electric vehicles, solar PV, UPS, etc. He is a senior member of IEEE and life member of ISTE. His research areas of interest includes power quality, power electronics and drives, electric vehicles, high-speed energy storage devices, artificial intelligence, deep learning, machine learning, solar PV, SMPS, custom power devices, PFC electronic blast, PFC LED driver, and PFC DC-DC converters, etc. So we welcome you, sir.
Thank you.
Yes, sir. So now you may proceed with your lecture.
Okay, thank you for introducing me with the target audience.
Yes,
And
sir.
I would also like to thank Dr. Nidhi for inviting me to share my knowledge resource pertaining to the wind energy conversion system. So I'm sharing my slides now.
Yes, sir. Sir, your mic is off.
My slides are visible.
Yes, sir.
Yes, sir.
So very good afternoon to all. I think am I audible? If there would be any issue, please let me know in between as well. Interrupt me whenever you feel like. So I would
Yes,
like
sir.
to thank
So PPT
Dr.
is, yes,
PPT
sir.
is
So PPT is not in presentation mode, it seems.
I have made it in presentation. Is it so now? Or still it is not in the presentation mode?
Sir, it's okay, but I think it is not in presentation mode.
But here it is, to me, it is visible as presentation. Now I have moved out from presentation.
Yes, sir. Visible.
But I'm
Okay, sir, you can proceed.
okay. Just a minute. So yes, the today topic for discussion is the wind energy conversion system, the current trends and challenges. So in this particular the discussion or the knowledge sharing, I would be discussing about the isolated as well as the non-isolated topologies, covering induction generator, the permanent magnet synchronous generator, and then DFIG, that is doubly fed induction generator. So these are the topic of discussions for today, and a few of the experimental results also I'll be showing you with the fluke canal power analyzer, the results being captured. So yes, if you go ahead with the overall ecosystem of energy in all across the globe, so energy industry is being divided into two categories. One is the non-renewable, the other one is a renewable, as everyone knows. So going to this two non-renewable and renewable energy sources, there are the technologies and the supplier who are associated and the equipment associated, and then at the end there would be consumers who are using these energies as the renewable energy sources or the non-renewable energy sources. So if you categorize, the coal and oil and gas are comes under the non-renewable energy. They are the fossil fuels, and in the renewable energy we have solar, wind, biofuel, hydro, then fuel cell, geothermal. These are comes under the category of the renewable energy. So since our topic of discussion today is wind, hopefully solar would be taken care by some other experts. So I'll be discussing only on the wind energy conversion system. So yes, the question comes that why we should looking for the renewable. Well, as the name suggests, that they do not deplete the natural resources. That is the first and foremost important point of concern. The second, they do not impact as the global warming, which we are aware that there are greenhouse gas emission due to the non-renewable energy sources, and which really depleting the ozone layer, and that will really impact the our overall environment. So we need to ensure the global warming, and you are aware that this time in the summer in NCR itself, the temperature has touched around 50 degrees Celsius. So yes, where we are heading towards, we don't know, because beyond 50 degree, it is very difficult to survive and things become out of control. So the other issue is how to why we should go for renewal, that we need to ensure the carbon footprint and even carbon dioxide emission to control the emission as maximum as possible, so that we can control the environmental pollution. Also, the other advantage is you can guarantee energy security for countries deploying it. That means there is the threat. Security threat is also being associated, that is energy threat. So that also you can ensure going with the renewable. And also the legislation being passed, making renewable more and more attractive. And also the cost of the energy per unit or per kilowatt hour is also quite lower in case of the wind as well as in the solar case. So yes, if you go for key renewable energy sources, we have solar, which is has two application, photovoltaic and solar thermal. If you go to the wind application, it has onshore and offshore application, and then we have an hydropower. So we are total focusing on wind power, onshore as well as the offshore, the wind mills which are being placed. Looking at the overall Indian power sector scenario, as per the data from Central Electricity Authority, Delhi, this as on 31st October 2016, the overall installed capacity of the Indian power sector is 308 gigawatt, And look at the pie chart. It is mentioning that thermal has a largest contributor, which is 61%. Then comes renewable, very recently has crossed the hydro, which is 15%, and hydro has 14%, and rest other are gas and nuclear, which is 2%.
So,
Yeah,
sorry,
please.
sir, sorry to interrupt. I think slides are not moving.
Oh, just a minute. Let me see. There is some issue, I hope. Please let me know. We are at a first slide. Is it visible?
Sir, I think it is not a first slide. It is fifth. It is sixth slide.
Okay. We have Indian power sector is visible to you?
Indian renewable sector is visible, sir.
Acha, Indian renewable sector is visible. Now I am just moving to the next. Can please check whether the wind is air in motion? Is it visible? The next slide, 7th slide.
Not visible, sir.
No, sir.
What's the problem is? Let me share again. Maybe. Please confirm whether 6th slide is visible.
Yes, sir. It is sixth slide.
And now I am just moving to the please confirm whether it is 7th slide now. Please
No,
confirm
sir.
whether it is a
It
no.
is sixth slide still.
Oh my God, what is happening? Just a minute. Now, please confirm, is it the first slide?
Yes, sir. It is the first slide.
Okay, now I'm just changing it. Please confirm.
Okay, sir.
Yeah, now it's second.
No, sir. Sir, if you share your entire screen, it will be, I think.
Let me do that.
Yes, sir.
So after sharing the entire screen, please minimize this window now.
Okay. Is it visible now?
Yes, sir. Now it is okay.
Yes, sir.
Moving as well?
Yes, sir.
Now I'm at slide number 3, 4, 5. Indian
Yes,
power.
sir. Correct. Sir.
Correct?
Yes, sir.
Okay, okay. Thank you. So yeah, I was discussing about the Indian power sector scenario where the thermal is 61%, the renewable is 15%, hydro has a 14% contribution, and rest other is in gas and nuclear. So this is the data of Central Electricity Authority as on 31st October 2016. Now, since our point of major discussion is Indian renewable sector, well, looking at the two major contributor, wind has taken a lead, which is having a 61% contribution as on date, that is 27.2 gigawatt, and solar is gaining the potential mostly in the Rajasthan and the eastern part. It is increasing. So it has currently 7.8 gigawatt, which is 18%. Rest biomass and small hydropower is having around 11 and 10%. So yes, if you can see, two are the front runner, wind and then the solar. And wind is gaining, really taking a big lead. But yes, solar is really catching up. So yes, going behind. I hope slides are moving now.
Yes, sir, it is.
Fine, fine. So if there would be any the screen is being freeze, please let me know. So yes, if we talk about the wind energy conversion system, it is basically wind is the air which is in motion, and that energy is being utilized for the moving the blades of the wind turbines or the windmills. There are two types of the wind turbines, whether horizontal or the vertical one. Both I will be showing you. So what is wind energy? Basically, it converts kinetic energy of wind to the electrical energy, basically through mechanical and then mechanical to electrical. So broadly serving as the choice of renewable source in Europe and the United States. So largely it is being used extensively in Europe and United States. Now the other Asian countries has also started using it because of the many benefits, which I'll be talking in the coming few slides. So increase size, you can increase the size and increase the productivity, which has really enabled wind generation to become an increasing competitive alternative to more traditional methods of power generation, which is your coal and the other means. So, well, the other issue is uncertainty is the main problem with the wind production, owing to the inherent unpredictability of the weather condition, because maybe the wind speed currently may be 10 meter per second, maybe after some time it may reduce to 6 meter per second. So that is not in our control. So that's why the unpredictability is there, and that really ensure that frequency variation. And whenever we are grid tied system we are talking about, the frequency is the major criteria which need to be ensured. And utilization of the wind generation is generally quite low, with in the range of 25 to 35% as the utilization rate. So this is more generic about the wind energy. If we talk about the wind power through windmills, the power is coming as a DC power, which is through the inverter and other interconnects, converted into AC of suitable frequency, which is 50 hertz for Indian case. In case of US and Europe, it is 60 hertz. Then through the main utility panel, it has been now through AC utility meter, it is being integrated with the grid, so you can inject the power as and when required. So this is how. And there is another system which is called battery energy storage, which is also gaining popularity these days. So we can have battery energy storage, and we can keep this storage in the battery, and we can use at the hour. If the very quite interesting phenomena in terms of the wind and solar is available in the day, and due to the natural geographical reasons, the wind speed is higher in the night time. So that's why they are both work as complementary to each other. Wind power generation is high during the night time, and solar power during the daytime, because sun is available during the daytime. So that's why both are working in complementary to each other. There are certain pros and cons with related to the wind. Well, smaller land requirement as compared to the solar and hydro. This is the added advantage. It can build offshore. Offshore means we can use the catchment area of the seashore, or you can say of the water bodies. We can place the windmills there, so that is called offshore. And if we can place the windmills on the any land area, then it is called onshore. It fluctuates less than the solar fluctuation. Solar irradiation fluctuation is more as compared to the wind fluctuation, and it is another biggest advantage is it is cheaper than solar. That's why you can see the contribution of the wind energy is more. If you talk about the cons of the wind energy, it is premium onshore sites saturated. That means wherever we can see the hilly areas or the coastal area where we can keep the windmills, those premium locations has already been being utilized. You cannot generate the new locations. Intermittency issue, that means the wind is intermittent in nature, so that is also creating an issue. Offshore towers are more expensive, so if you are putting up in the water bodies, then those are quite expensive. Energy storage is not considered to be a very viable solution, but yes, at the research level and at the few real-time application level, battery energy storage system has also been used. The other issue is it create a noise pollution as well, which is not the case in case of solar. So these are the few pros and cons of the wind. Well, if you're looking at the generic nature of the wind energy, it is the fastest growing energy source, and it is considered to be the clean and renewable energy source that has been used for the centuries in Europe, and now more recently, United States and other nations are also being using very extensively. In today's world, well, wind is one of the cheapest and the cleanest energy source. So that's why it is gaining more and more popularity. Well, giving more statistics to sharing to you, the worldwide capacity is reached around 435 gigawatt by the end of 2016. The highest contribution was done in 2009, which is around 38 gigawatt. The wind power showed a growth rate of around 31.7% in 2001. Asian countries has largest share of new installation of around 40.4%. North America has the highest as an individual capacity is 28.4%, again because of the geographical locations. And Europe in this race has gone up to the third place, has a contribution of around 27.3%. If you talk about the Asian market, well, total installed wind capacity has gone up to 40 gigawatt, which is around 10% of the global capacity. And looking at the Indian scenario, the wind generation was around 28 megawatt as on 16th April. But now currently, if you talk about the latest data of April 2024, we have reached up to 46 gigawatt. So this is the current scenario of the wind power generation installed capacity of 46 gigawatt in India. If you look at the perspective in terms of the different states, how they are contributing, Gujarat is the leader, which is around, I think, 27-28%. I'll be sharing you in the, I think, next slide. So wind power capacity in India has increased significantly in recent years, only because of the cost of electricity or the power is quite lowest in comparison to other renewable sources. The majority of India's wind power capacity is in the western, southern, and the northwestern states because they have more potential of the wind and the coastal areas. The government of India has launched initiative to promote wind power, including the National Wind Solar Hybrid Policy. So they have developed a National Wind Solar Hybrid Policy by which they are offering certain kind of benefits so that more and more private ventures can come forward for establishing more and more windmills. Wind power, as I said, complementary to the solar power, as wind power is most productive at night and solar power is more productive during the day. So they can work in tandem. There is no competition parallel to each other. MNRE, Ministry of New and Renewable Energy, has a program to promote development of renewable energy research and technology. So MNRE is giving a lot of schemes, offering many schemes for research in the area of renewable energy, and they are offering the funding as well. This is what the wind power installed capacity as per the data of April 2024 from the MNRE. The highest contributor, as I said, Gujarat is 25.53%. The second in this category is the second state is Tamil Nadu, which is around 23%. Karnataka is 13.5%. Then the other two states are in two digits, Maharashtra 11.3% and Rajasthan, both are at 11.3%. Rest other states are in single digit number. So this is how you can say the contributors. Obviously, looking at the coastal area, highest wind penetration is available. So Gujarat and Tamil Nadu and Karnataka are the leader, and even including the Maharashtra as well. Well, this is what I was talking about. There are two kind of wind turbines or windmills are there. One is horizontal axis wind turbine, and the other one is the vertical axis wind turbine. So depending upon the requirement and the wind flow, we can keep uh, as per the terrain, the flow of the air, the penetration of the air, the velocity of the air. We can keep any one as per the requirement. This is one of the vertical axis turbine, which is in Quebec, Canada, installed in 1984, and the power rating was 3.8 megawatt. The manufacturer was Wicker. Well, as far as the motivation why we should move towards the wind turbines and wind power generation, well, first of all is the energy crisis, as we are ensuring that the fossil fuels are depleting with a much faster rate. Maybe in next 30-40 years, so you may not able to see the availability of coal for thermal power generation. So, or maybe it may be depleted maybe much faster than that. So that's why this is the first issue that we need to look in terms of the future requirement, the other options. So renewable is the best option. Then the other one is the escalating prices. The prices have been escalated like anything for the coal and the fossil fuels. So that way also the cost of energy is increasing. So that's why we should move towards the renewable energy. The other environmental issue, looking at the NCR region, well, you are already aware that post-COVID, the smog is the biggest issue during the winter season and during near about the Deepavali season. The smoke and the fog combination really creates the big havoc, and you people are finding very difficult to really breathe properly and inhale the pure form of the air. And AQI, air quality index, as you are looking at, is really crossing the danger mark more than 200, 300, and sometime during the Deepavali time it has gone up to even touching the 4-digit number around 1000, which is really very harmful for our body. So the greenhouse gas emission is the one problem, acid rain is the another problem, water pollution. So there are many environmental related issue with the other power generation sources which are not renewable energy sources. So that's why looking at these two major issues, we need to look for the researcher should work towards the more and more contribution from the renewable energy market. Well, there are standalone system where grid cannot able to reach. We can design isolated system, but not grid tied. But yes, it is always being preferable that we can have a grid integrated wind energy conversion system. So, what are the challenges for the grid integration of the dispersed wind energy? Highly variable wind power injected into the grid. So we have to maintain the frequency, because for parallel operation, the most important factor is the frequency, and variation is not allowed more than even 0.5 hertz. So that's why that is the most important thing. Increase penetration of the wind energy. Well, again, it is not in our control. Then electrical weak distribution network. Our network system is mostly radial structure, and due to the large R by X ratio in the distribution line, the losses are also quite high. So that is also a bigger challenge in our distribution sector. And since we are using induction generator, well, it can increase the burden of the reactive power burden because it's a highly inductive load. So your reactive power requirement will increase, and obviously it will impact the power quality. So that's why that has to also be ensured. This is the basic system description. If you talk about the infinite bus, then we have in AC system we have a transformer T1, T2, T3 at different stages, a step up and a step down. For as we all know that our this electrical network is divided into generation, transmission, and distribution. So we have to use both power transformer and distribution transformer for a step up and a step down purpose respectively. And then we have a load line. Loads are being connected at the point of common coupling. So load line 1, 2, 3 loads will be connected, and then we can connect a WAX, which is a wind energy conversion system, to provide the additional requirement of the power, or maybe to ensure that the available power from the wind can be utilized so that less load on the grid. And then induction motor, as you see that induction motor is most widely used motor in the industrial application. So all these loads, and then NNL is a non-linear load. I think almost all the loads in electrical are considered to be non-linear load, and because of which the reactive power requirement is increasing, and that's why our power quality parameters like distribution and distortion factor, displacement power factor, efficiency, these are really severely being impacted. So we need to ensure that we should, while connecting these non-linear load, the supply should not get polluted. So from source, we should they are providing a clean voltage supply, so we can able to extract the clean current, because whenever you connect a non-linear load, certainly it will draw a peaky current which is loaded with so many harmonics, and because of which your THD, total harmonic distortion, increases like anything. And as per IEEE 1159519, there is a limitation that more than 10 ampere current, your THD must be less than 5%. So we need to ensure those international standard as well, whether it is the IEEE standard we're talking about, whether we are talking about IC standard. So this is a synchronous generator with rotor excitation. This is the largest wind turbine installed in the worldwide. It is a variable speed wind turbine made by the manufacturer Ircon of 6 megawatt capacity. This is a PMSG based, permanent magnet synchronous generator based wind turbine installed in 2004. It is multi-bird grid company of 5 megawatt. Just showing you a few pictures of the installed windmills. This is the basic fixed speed. We have a variable speed induction generator as well as the fixed speed. So once we are talking about the fixed speed, then we have a gearbox, then a squirrel cage induction generator, then we have a soft starter, then we have a capacitor which is ensuring the power factor, that is reactive power compensation, then we have a transformer, then we have a grid. So this is a power flow can be done in one unidirectional from windmill to the grid. In case of DFIG, we can have a bidirectional power flow. That is also the advantage. That's why DFIG is gaining popularity these days. So in this system, we have a gearbox, cage induction generator with direct grid connection. Then we have a soft start and then capacitor for the power factor compensation or the reactive power compensation. For the fixed speed induction generator, well, there are certain advantage and disadvantage. If we talk about the advantages, it is simple and cost effective. The maintenance wise also it is quite on the lower side, but there are certain drawback. Its wind energy conversion efficiency is pretty low. Poor power factor, that means power quality is very poor. Power fluctuation in the output, high mechanical stress on the turbine component. So that's why fixed speed induction generator are these days are rarely being used. PMSG and DFIG are being extensively used all across the globe. The second comes the variable speed wind energy system with MPPT. The same way you are in the solar, we can have an MPPT. Similarly, in wind also we can have a maximum power point tracking in the your grid interfaced wind energy conversion system. So I'll be discussing about this is the certain calculation which is ensuring that which are the formula and how much the wind energy can be converted into electrical energy. So if you see the wind energy conversion machine convert wind energy into electrical or mechanical form. So the formula basically is power is kinetic energy, half mv square upon time, and mass upon time is given by density into area into velocity. When you merge these two formula, you get a formula of half of density into area into velocity cube upon 2, half of density into area into velocity cube. With this, you can able to decide that how much power can be generated. So just for your understanding, let's say the wind speed is 10 meter per second, area of the blade is 2 meters square, and then the density is 1.2 kg per meter cube. By putting these values, we are getting 2400 Newton meter per second, which is watt. So this is the ideal figure. That means we can have 22.4 kilowatt power can be generated with the data of this velocity, area, and the density which we have. But this is not the actual figure. Actual figure is given by the Bed's limit, which says that only 59.3% of the theoretical is the maximum amount of extractable by the wind energy conversion devices. So in place of 2400 watt, you can only get a 59% of that, which is practically possible. So that's why only 1.42 kilowatt in place of 2.4 kilowatt we can able to expect converting that wind energy into the electrical energy. So this is given by the scientist Betts, so that decide the limit of around 59.3%. Well, as I said, this is the one of the most important criteria, that maximum power tracking in the grid interface. So in order to operate at maximum power output of a wind energy conversion system, it is necessary to drive the wind turbine at an optimal rotor speed for a particular wind speed, which is normally considered as lambda, which is tip speed ratio. So what are the major point of consideration for MPPT drawing the maximum power point? We need to know the wind speed. We should be aware about the rotor speed. We should know the rotor characteristic, and we should also have generator characteristics. So these are the 4 important parameters which we should aware, and their graph should be aware. Then only you can able to extract the maximum power tracking. So if you can see, there are 3 graphs. One is in yellow color, then the other one is in the purple color, then one is the you can say black color, which is a black or a brown, you can say. These are the sinusoidal kind of a curve, half sinusoidal kind of curve. These curves are normally considered as a rotor curve. And then you see a vertical line. These are the vertical lines near to 1. This is considered as a mechanical input power curve of the generator according to the load curve, and the dotted line is considered to be electrical load curve. So initially, first operating point, as you can see, if this curve, the mechanical input power curve, is cutting this particular curve, that is your 7 meter. The brown one is 7 meter per second. You can say the other one is the 8 meter per second. The yellow one is a 9 meter per second. Purple one is a 8 meter per second. So these are the 3 different speeds. Rotor speed or wind speed, you can say, it is being decided. Now wherever it is intersects, that is the first operating point. Now we need to move towards the peak area of this, that is called the optimum operating point or the maximum power point tracking. So how this can be done? This can be done by adjusting your electrical load on the generator. So that way we can shift this operating point towards the optimum operating point at a particular wind speed. So that is, if it is 7 meter per second, we should move towards here. If it is your 8 meter per second, we have to move towards the peak point of this. So this is how we need to adjust, so that, and that can be done with your control scheme, so that the load at the electrical load at the generator should be decided, so that you can always extract maximum power which you can extract from the wind energy. So this is the 4 characteristic: your rotor speed, your wind speed, rotor characteristic, and your generator characteristic. These are the 4 characteristic must be known in advance to you, and where the graph is power on the y-axis and the rotational speed are in RPM in the x-axis, can able to help you to extract what kind of a control scheme. Because for any system, the major point is your control scheme, how you decide your control scheme, whether it's a digital control or the analog control, and then how you adjust so that your PWM, pulse width modulation, being given as a switching pulse to your IGBT, should be adjusted so that you can extract the maximum power tracking. This is the another graph which is known as the aerodynamic characteristic for the wind turbine characteristic. It is also a graph between turbine speed on the generator side in RPM to the power on the y-axis. And here 2000 kilowatt is considered as 1 per unit. And now you can see this graph is again drawn for different wind speed, starting from 5 meter per second to 12 meter per second. Again, you can see at a lower RPM, at a lower turbine speed, you are not able to achieve the maximum. Maxima is being achieved somewhere close to the midway. So if you see 5000 RPM to 3000 RPM, somewhere close to, you can say 1500 to 2000, you are getting a maximum. But beyond that, if it is increased, then your friction, air friction, and then the bearing and the other losses increases. So the graph is start decreasing. So you need to, again, your graph should be such that your power tracking should be such that you are touching the maxima point, so that you can achieve the maximum power tracking. And that is the role of your control algorithm, control strategy, so that you can extract the maximum power. So why is MPP controller not perfect? If you are not able to design a perfect MPPT controller, there could be a few reasons. One of the major reasons, the rate of change of the rotational speed is limited. Then again, you can't able to decide. Wind turbine output is interlaced with the wind mechanical or aerodynamic power and the rate of change of stored energy. If you are storing the energy, and if your rate of change of stored energy is changing, then also it is very difficult to design, because controller should be given the data in the proper pattern. That's why lookup table is being designed, or you can generate the data so that on that pattern your controller can work. So that's why you need to have there could be a variation in the your wind, but it has a proper pattern to be followed, and then that should be given in the lookup table, and then you can really train your control algorithm so that your PWM pulses can be generated in accordance with it. Then how much time, response time, would be taken by the MPPT mechanism? This is a basic governing equation which we talk about, d omega upon dt, where omega is the angular rotation in radian per second. Ta is the mechanical torque generated by the wind rotor, which is a function of the velocity, angular velocity, and the your wind speed. Then we have restoring torque of the generator, which is the function of two currents, direct axis and the quadrature axis current. Then we have a torque due to frictional losses, which is due to the generator and the gearboxes, and which is the function of the rotational speed omega. And J is basically moment of inertia of all the rotating parts. So this is a governing equation. If you want to calculate the time, you just have to get dt on the other side, the other factor on the cross multiplied, and integrate. So you will get the ideal response time of the MPPT controller. Because whenever we design the MPPT controller, this is the time which is 0 to 2 dt, and that will be omega 1 to omega 2 for the particular variation of the speed. If these factors are well known to you, you can calculate that how much time with the change in the speed, your maximum power point tracking should be again trace as per the your controller design. So that is how much time. That's why you need to design a controller so that it should be fast in responding to the change in the wind speed. So wind speed forecasting, well, for that forecasting you have two kind of a model. One is a linear predictive methods. So wind speed time series data typically exhibit autocorrelation, which can be defined as the degree of dependence on preceding values. So you can have that linear, you can say forecasting or prediction you can do. So those autocorrelated time series models are commonly used for wind speed prediction. So one is time series prediction, where forecasting can be done. The other one is a neural network for wind speed prediction. It is called neural network because it is a network of interconnected elements, and it is inspired from the biological nervous system. And neural network can train to learn sequential or the time varying pattern. So you can have the wind speed forecasting can be done, because this is required for training your control strategy so that the PWM can be generated as per the variation of the speed. So how can the time series prediction to be used for improving the MPPT mechanism? Well, response time and control algorithm, these are the two important factor, that how fast it is responding, your control is responding, and what kind of control algorithm you are using. So d omega dt can be controlled to extract more energy if future wind speed value is known. So that means if the future speed is known, then you can control your you can extract the more energy through MPPT. And dw by dt is adjusted to achieve predicted optimum value while synchronizing with the optimum actual value. So that means we should be in a position to know the predicted value only. That's why we need to design a lookup table. On that basis, we can start tracking as per the variation of the wind speed. We can start tracking your maximum power. So for tracking performance, as I already said, there are four things are required, which is wind speed, rotor characteristic, and generator characteristic to track Sorry, there was a power cut here.
No problem, sir. You can continue the lecture.
Yeah, just a minute.
Yes.
Is it visible? Slides are visible?
Yes, sir.
Fine. So I don't know where it was being stopped. So I'll be taking from the variable speed. There are you can say three kind of a generator which can be used. First is the induction generator. So I'm just moved little 4-5 slides back actually. So one is variable speed turbines with full converter. Full converter, why it is being termed as full converter? Because it is connected through the stator of the induction generator, where you can say the first is your wind turbine, then your induction generator, and then your AC to DC converter, and then you have a DC link capacitor, and after that DC to AC. And here it is being given suitable voltage and frequency, and after a transformer, the voltage has been stepped up as per the level of the grid so that the parallel operation can be done. So here these two stages, first stage is DC to AC, then is stabilizing the DC and then converting DC to particular AC of a suitable frequency. So two stages are being there, and in this case for the two stage The major challenge is if efficiency of any stage is lower, or rather much lower. Let's, for example, one is 90%, that is 0.9, the other one is 50%, then the product of these two will be less than 0.5. So whenever two decimal number have been multiplied together, the product will be lesser than the smallest number. So that's why it would be 0.45 only. So that's why whenever you connect multi-stages, it is important that both converters, both power electronics converter must have very close to each other efficiency to achieve a same amount of efficiency. So for to countering this particular, you can say, issue, these are the advantage, disadvantage. For countering this particular issue, the matrix converter, which is AC to AC converter, is being used in place of AC to DC and DC to AC converter of two stages. So matrix converter is have direct one conversion, so you can really improve upon the efficiency. And the second is the cost also reduced, because one stage completely you have removed. So in place of two stage, you have only one stage. And it provides a large number of control levels that can allow for independent control. So you can have different levels you can also achieve using the matrix converter, because you have controlling AC on one side to the AC on the other side. So you can control both voltage, frequency, phase angle, everything you can control, and you can maintain a good input power factor as well. So the only challenge with this is the control is a complex. For matrix converter, it is a quite complex control. So if you look at the advantage, it can eliminate the DC link reactive component. So DC link capacitor, which is of quite costly, and it should be at a higher power rating. So that's why that can be completely eliminated. This is the best advantage. Compact solution and yield high input and output quality. So that is also the advantage. A smooth grid connection. Grid connection can be done is very smooth, because you can have a control on everything. No requirement of the your DC stage here. And secondly, low voltage ride through capability. So you can go as per the wide voltage range variation also can be achieved. So the major disadvantage is complex control, and then this technology is yet to be matured. So it is not fully matured as on date, as far as the real-time application is concerned. At the research level, it has already been matured. So this is the another, you can say, circuitry where which is talking about, first is wind turbine, then you have a 3000-watt induction generator, then star connected capacitor for reactive power compensation, then you have a 3-leg PWM current source converter on the rectifier stage. So it is controls your current source rectifier. Then we have a inductor to control your current ripple currents, and then we are converting into DC into AC using PWM current source inverter. So it converts DC into AC. So this is how it can be converted, and then using the transformer, you can connect it to the grid. And again, on the other side, you are connecting the capacitor for the reactive power compensation. So this is how you can control. But since these all are control devices, IGBTs, so that's why you need to provide the pulse at the gate terminal, and for which you require a control algorithm or control strategy, which is the most important part. So this is one of the control strategy if we talk about for current source converter on the one side. So if you see here from this side, we are sensing theta of your rotor, and then d by dt, if you apply it, is omega angular velocity. And then this theta are also going through ABC to DQ transformation. So we can generate a voltage template of voltage direct axis and quadrature axis on this, on your stator side. Similarly, and then once you are sensing this, then through the torque for MPPT, your electromagnetic torque you are taking from here, then dividing with the 1.5 into NP into lambda r, which is a tip to speed ratio, you are getting a quadrature reference current. Similarly, from the omega r with connecting a field weakening block, you are able to get a reference direct axis current. Then both you are converting from Cartesian to the polar coordinate, and then comparing with your actual current sensing from here. And from this, you are converting this again into alpha r, theta r, and alpha r is being compared. That will give you theta omega r. And then finally, as per their angle, this PWM pulses has been given. And normally for 3-leg converter, same leg, if 3 pulses you can generate, you can connect a 3-NOT gate so that you can get a complementary PWM pulses, because the logic is in the same leg, two semiconductor devices should not be turned on together. So it's always in one leg top group, and then from any of the other two leg, the lower group device should be turned on. So this is normal 3 ways implementation of the converter. So this way it is being implemented. Similarly, on the other side, the PLL will be implemented. Then again theta and then VPI has to be taken. Then reference voltage through the PI controller has to be passed through it, and then reference voltage is being divided by cos inverse to get alpha, and then alpha and theta is being compared to get the PWM pulses. So this is how you can get this particular control scheme, because this is required to provide PWM pulses. As you can see here, the PWM blocks are there, which is basically to generate PWM pulses for both CSC as well as your rector size convert. So this is how you can generate. But here power factor is not being ensured. For ensuring the power quality or power factor, you need to change this side, that is AC side, your control scheme. So if you see the power factor control with CSR and CSI, what changes has to be done here? You need to ensure that you need to convert this same block which you are converting here, you can put it here as well. That means Cartesian to polar, current sensing, comparing. You need to compare current, reference current to be generated, and you have to compare with the actual current. And whatever error signal has to be generated, it has to be passed through your PI controller, and you can control your error, and then it has passed through the PWM converter with that particular error with the sawtooth waveform. So once both side, if you do, then you can have a power factor and this side as well as CSI side as well as the CSR side. But in the earlier scheme, it is only controlling the power factor at you can say grids, not grid side, towards your turbine side, but it is not ensuring here. So both ways, if you are doing, then you have to change. Both have to make the similar one. So this is control is considered to be the heart of any particular your system, because it has to generate the PWM pulses as per your requirement. Now, if you're talking about this is the practical application. This is the 1.5 megawatt you can say wind turbine, which is the manufacturer was GE Energy, and it is with DFIG, doubly fed induction generator. So now I'll be discussing about the next one is the DFIG, doubly fed, because here we are stator also power is being fed from stator to the grid, and then from the grid the power is being injected back to the rotor, that is at a slip frequency, because at the rotor the voltage is of slip frequency. So that's why now it is not the full converter, it would be at reduced power. So that I'll be showing you. This is another offshore you can say first offshore wind farm in UK, which is of 2 megawatt. Vestas is the company, and it is with the generator is DFIG, doubly fed induction generator. Now you can see there are so many windmills have been placed in the offshore. This is the largest wind turbine with DFIG, which is 5 megawatt of RE power, and it is with the generator is doubly fed induction generator. Now this is the basic system diagram in which you can see one power flow is happening from windmills to gearbox to doubly fed induction generator, and from stator the power is going to this 3-phase transformer and to the grid. But from the transformer you can also inject the power to the rotor. That's why it is called doubly fed. So from AC to DC, then we maintain the DC link voltage at the capacitor, and then DC to AC of reduced frequency. That means at S times of the fundamental frequency, it has to be converted. So it is at reduced voltage level. It is being injected at the stator. So that's why this is the converter. Both the converter are at reduced capacity converter. That's why the losses are less and cost is also less. And that is what the additional advantage of doubly fed induction generator. Although control may be a little bit complex, but it can really work on large variation of the speed, because here we are getting a slip frequency. So that way we can control large variation of the voltage you can control. So DFIG system, it's a variable speed range, 70%, that is sub-synchronous speed to super synchronous speed, 130% of the synchronous speed you can achieve. There is a gearbox, and then power flow can be done in bidirectional. It can flow from rotor to the grid as well as grid to the rotor. So it has bidirectional back-to-back converter is being connected, and you can also ensure the maximum power point tracking here. And currently, because of this advantage, cost and then the low power rating, it is being extensively used in the industry and the real time. So reduced converter cost, as the converter rating is typically only 25 to 30% of the total system power rating. So that is the major advantage. It can improve efficiency due to reduced losses in power electronic converter. So efficiency also can improve to the large extent because your power electronic converter, which is being used, has much lesser rating because of this. Your voltage is only as times, slip times of the your frequency. Suitable for high power application, including recent advances in offshore installation. So mostly the offshore installation and for high power rating, this is being preferred. And the other problem is bidirectional flow of reactive power. You can flow the reactive power in either direction, whether towards your turbine side or whether towards the grid side. High fault ride through capability during network disturbances. You can really control the power flow. So that's why once there is a network disturbance, to control the frequency, another thing, you can have a very precise control. And it is also flexible for 4-quadrant operation. Since you can have a sub-synchronous speed, super synchronous speed, so it can operate both as generator and motor for sub-synchronous. It can also operate for super synchronous speed in the motor and the generator case. So that's why it has a wide variation in terms of the speed as well. This is the actual diagram. If you can see, this is your wind turbine gearbox. It's a DFIG. Then you have a rotor side converter, 3-phase converter. Then you have a DC link capacitor. Then you have a grid side converter. You have your inductance controlling the ripples in the current. And then you have a transformer, and you can feed all the 3 phases to the grid side. And now the power can flow in either direction. And one power is already being flown from stator side to the grid. So that means it's a doubly fed induction generator. This is what the concept is all about. And it can support a large variation in the wind speed as well. So the principle of operation, what is the principle of operation? The frequency of the grid voltage is always maintained constant, irrespective of the wind speed. Thus the rotor speed or by the back-to-back converter. So this is, you can have a wide range of variation, and you can maintain a constant frequency, which is a major requirement for the parallel operation or the grid connected system. By using converter to control the rotor current, it is also possible to adjust the active and reactive power. So since you are flowing the power as per your control in either direction, you can both active and reactive power you can control to the grid from the stator and independently of the generator turning speed. And at sub-synchronous speed, which is lower than the synchronous speed, the stator is generating the power, but part of it has to be fed back to the rotor. So that means you can feed back the power to the rotor as per the requirement. And at super synchronous speed, both rotor and stator are producing power to the grid. So super synchronous speed, we are feeding full power to the grid, and sub-synchronous speed, some power from the grid is feed back to the rotor side for a better power quality control and frequency control. The current rating of the rotor converter is defined by maximum active current required for the torque production and the maximum reactive current required to magnetize the machine. So that means since we are working at a lower voltage level and lower frequency on the rotor side, we are having less stress on the converter side. And if all magnetizing current is supplied by the rotor winding, the stator will only have a torque current, and so you can have only, it has to ensure the torque necessary current generating for the torque. So you can inherently you can maintain a unity power factor. So that's why power quality can automatically be maintained for a larger speed, wind speed variation, and for a larger DC link voltage as well. This is what the advantage with DFIG. So what are the available control strategies in wind driven DFIG? The primary control objective to maximize the power capture in sub-rated condition by using the maximum power point tracking. So it is best suited with DFIG, the maximum power tracking with all variation of the speed from lower to the higher. Limit the rotor speed in the rated regime, so it can control. You can rotor speed because you can flow the power in either direction, from rotor to grid or grid to rotor. So you can limit the rotor speed, and you can control the power factor at all times. So you can have a full control on the power factor and THD for large variation on either side of the speed. So that is for the large variation of the wind speed. So this is what the advantage is. So as I said, there are two kind of converter: rotor side converter and the grid side converter. Which is close to the grid, it is called grid side converter, which has purpose to convert AC into DC, and which is a rotor side converter, it is for DC into AC. So that's where you can control both sides. So RSC is basically which is responsible for controlling the torque and the flux of the machine. RSC rotor side converter can also have active and reactive power flow of the machine, and it is also responsible for MPPT. That means you can have sharing their requirement and their load. So MPPT will be taken care by RSC, and unity power factor will be taken care by GSC. That means grid side converter. So grid side converter maintain the DC link voltage constant irrespective of the region of operation, in which region we are working, whether sub-synchronous speed or synchronous speed or super synchronous speed. It can maintain a constant DC link voltage, and it can also ensure unity power factor operation for either direction of power flow. So power whether flow from grid to the rotor or rotor to the grid. So you can, because of the rotor side converter and grid side converter, you can really have an independent role, and responsibility can be decided depending upon the control, because separate control will be there for RSC and separate control there for the GSC. So you can really divide the work, and you can achieve your objectives. So that's why DFIG is gaining popularity from past, you can say, almost a decade or so. So there would be an inner loop control, which is rotor currents, and outer loop control variable will be electromagnetic torque, your static power, your total active power, whether it's stator and rotor active power, then air gap power, which is called electromagnetic torque multiplied P equals to omega into PV, which you used to say. So electromagnetic torque multiplied by rotor angular speed and the rotor speed. So you can have two kind of loop can be decided for RSC. One for inner loop, where rotor currents has to be ensured as a control variable, and in case of outer loop, your torque, power, active, reactive, air gap power, and rotor speed can be taken care of. So this is how the control can be decided. You can have omega angular speed in per unit pass through the P controller, active power controller, so it can generate the rotor side quadrature reference current. Then your reactive power reference value and reactive power measured current can pass through the Q regulator, and it can generate the rotor side direct axis reference current. When direct and your mux, that they will be mixing together, it will give you a rotor side DQ reference current, and then actual three-phase AC current has to be sensed, and by the ABC to DQ transformation, it can convert three-phase to two-phase, and then you have your actual IR rotor side DQ current, and then your reference current and actual current. Once you pass through the current regulator, which is PWM, your converter, then you can generate the PWM pulses for the RSC converter, or three pulses you can generate. Connect the NOT gate with all the three pulses, you can get another three pulses. So this is how you can generate. And the equation which is required, so it is basically KP and KI. You need to tune it, and you need to decide the PWM pulses width in accordance with this. So this is just what has been done. And similarly for grid side, it has inner loop will be rotor current, outer loop will have two things only. One is DC link voltage, thus the power flow from to the grid, or to from grid to the rotor. That is the one objective. And second objective is reactive power should be coordinated with the RSC to maintain unity power factor. So you need to ensure the whatever the reactive power required by the system should be supplied by this grid side converter. So this is the control which is being done. Since we are controlling the voltage, so voltage has to be sensed, reference voltage, and then whatever the PG reference is being then your reactive power reference pass through the grid current calculation, then your grid current reference and quadrature and direct axis will come, both will merge together, and then actual current will be sensed, and it will be passed through the current regulator. And these are the equations which is to be implemented in these controller, because these are the block diagram which has been shown. So again, three pulses you can generate. Connect the NOT gate, so you will get the complementary pulses, and one actual pulse and one complementary pulse should be connected to one leg of IGBT. Similarly for the remaining two legs. So this is how to be done. This is what the objective which we are controlling the DC link voltage and controlling the reactive power. So this is how it is to be done. And actual implementation is being done like this. This is the grid, this is the DFIG, and this is ABC to DQ conversion. Then voltage sense, then it is P and Q, active power and reactive power. Then it has to pass through the PI controller, then inner current loop. Then this is the PWM generation. It is to be given, all the 6 pulses for the 6 devices. Similarly, for GSC side, it is inner current loop. Then all the actual current has to be sensed, converted into DQ, and then through the actual current, actual voltage is being sensed, compared with the reference voltage, passed through the PI controller. Then reference current generation with the actual voltage sensing, and then inner current loop has to generate the pulses for your PWM signal generator. So this is how the actual implementation can be done for the complete control scheme. And this is what the simulation result, if you talk about. So this is the performance of 2 megawatt. This simulation is being done on the MATLAB. It is a 2 megawatt DFIG based wind energy conversion system. In terms of, the first is your stator voltage, ABC stator voltage. Then you have a grid current. Then you have a rotor side converter current. Then stator current, rotor speed. This is omega R. And then you have a DC link voltage. This is VDC, is the DC link voltage. Then you have a active and reactive power at sub-synchronous speed. So since 10 meter per second is considered as synchronous speed, so less than that, so it is 8 meter per second. And the rotor speed is, which is 0.9 per unit comparing to this. So this is your sub-synchronous speed. So you can see here, perfect sinusoidal voltage is being there, and your grid current is also being sinusoidal. So that means you can say your grid side as well as your converter side. your CSC on the grid side as well as on the RSC, rotor side as well as the grid side, both have been maintained perfectly sinusoidal, and your speed is being maintained throughout constant, and DC link voltage around 1200 volt is being maintained throughout constant, and your power around 1.2 per unit is being maintained, and the reactive power, as you can see, is throughout 0. So this is what we know. We need that the reactive power need to be compensated to ensure the power quality. So this is how the simulation results can be captured from 1.8 second to 1.9 second. Similarly, at super synchronous speed, which is a 14 meter per second of 1.2 per unit, all the results, as you can see, it is almost some small, you can say here, your high frequency, your harmonics are there at the top. Some your disturbances are there, but it does not disturb the overall shape. That's why your power factor is being maintained throughout. Similarly, you're on the grid side as well as on the rotor side, it is being maintained throughout, and your speed, power, and the DC link voltage is being maintained constant throughout. This is what our objective. And then going to the synchronous speed, that is 10 meter per second at 1 per unit. Again, you can see that all these AC voltages, current through the grid side, current through CSC, current through your rotor side is being perfectly maintained constant, and sinusoidal as well, and DC link voltage throughout maintained at 1200 volt, and reactive power is MVAR at the last graph is completely 0. So this is what ensuring that you ensured the power quality, what is being expected along with your requirement of the power generation from the wind energy. And now if you can see the comparison, the 2 megawatt wind energy conversion system with 2 megawatt DFIG and 2 megawatt wind energy conversion with reduced power rating, your DFIG. So as you can see, once you take a DFIG less than the overall wind energy conversion system rating, your efficiency can increase, because your losses at rotor and your converter side, your losses will reduce. As you can see here, P converter losses here, P rotor losses are 0.0083. Here, P rotor losses are 0.01. So double zero, after decimal, you are getting double zero. So if you make the comparison of both table, your rotor side losses, your converter side losses, your stator side losses, all have been reduced up to 2 decimal, up to 2 after decimal 2 zeros almost we are getting. That's why efficiency of conversion efficiency in case of reduced rating DFIG, if you are using, it can go up to 96 to 97%, while in case of same rating DFIG and wind energy conversion system, it is going around 81 to 86%. So this is why we need to use a reduced rating DFIG to achieve a better efficiency and less losses in the power electronics converter. This is just showing the comparison of input power and the output power and the efficiency of both system, 2 megawatt DFIG and 1.5 megawatt DFIG. This is some other control scheme. I may not be, because of the time limitation, I think I may not be able to go much deeper into that. But yes, the moment you change scheme, you hardware, D space or microcontroller or TMS, you can say controller. Then certainly you can get it Texas Instrument controller if you use, which is very you can say now it's very cost effective. Hardly you can get the board, Texas Instrument board, hardly in 5,000. Earlier it was around 40 to 50,000, now in 5,000. So you can dump your program, your control algorithm, and you can generate using the optocoupler circuit and signal conditioning circuit. You can generate. So this is just I'm rushing through. This is a few other control algorithm. These are their equations which can be utilized. Again, as you can see, this is your maximum power point tracking curve. So we need to at a different speed, 4 meter to 14 meter per second. The red dotted line shows that we need to ensure that our operating point should move on this red dotted line, so that for any particular wind speed, you can always achieve maximum power, maximum output power from that turbine. So that is tracking the maximum power from the wind energy. So that is to be ensured. This is again, certain simulation results have been shown at a different speed. Sorry. This is at 6 meter per second. You can see all the three colored waveforms. So it is, once you make a zoom of these waveform, this is perfect sinusoidal waveform, which ensures that at the input side, your currents are perfect sinusoidal, which ensures the high power factor of the input side. Similarly, at 12 meter per second, still your waveform has been maintained, and your power required is also constant. Your DC link voltage at 1200 volt. Here also 1200 volt constant. Here also 1200, but here speed is 12 meter per second. So this is if your varying between 6 meter to 12 meter per second, your still current magnitude is increasing because you have increases the speed, but your current is remained perfect. All three phase current is being maintained perfect sinusoidal. If you zoom this portion, it looks perfect sinusoidal, which ensures the high your input power factor is being maintained on the AC side. So this is what our requirement, that power quality should be maintained. This is just a comparison that how the power is being flown from stator to the grid, or maybe grid to the rotor. So negative sign ensure that power is being taken by the rotor till here, and after that the rotor is also supplying power to the grid side. So both are supplying power on this side. That's why sum of these two is equivalent to this. So stator and rotor both are power flow. In case this side, the grid is giving power back to the rotor at a lower speed, subsynchronous speed. So this is graphical view for when the power is being PS is the stator power and your grid power. So when grid is giving power, so this is the point at 800 kilowatt. The power change has been took place where grid is giving excess power to the rotor side, and before that it was taking power. This is power fed to the grid at different speed. What are the different level of power is being fed to the grid? This is being given in the different speed, starting from 2 meter per second to 14 meter per second. This is one of the place in India called Jakau, that why we should go for a DFIG. If you see here, the wind speed is 3.1 meter per second to 8.75. This is a practical data from the site itself. From different hours, this data has been taken, and this is the speed. And DFIG, if you see the power generated by the DFIG and the energy generated by DFIG, and this is SCIG, squirrel cage induction generator, and this is energy, you can see is a huge difference. The energy generated by SCIG is 7,180 kilowatt hour, and rather here it is 10,950 over you can say different hours if you taken. So that's why DFIG is more efficient and it can generate more power. So that's why DFIG is gaining popularity all across the globe. So if I just summarize this summary of existing control in the grid interfaced wind energy conversion system. So PMSG, if you are using, it can have converter, can have diode bridge or SCR inverter. The control is simple firing control can be used. If you are using SCR rectifier or SCR inverter, then you use the firing angle control on both converter. If you are using diode bridge or hard switching inverter, then we can use a power mapping technique, including stator frequency derivative control, that is MPPT or wind prediction control. If you are using diode bridge or DC boost or hard switching inverter, then you can use vector control of supply side inverter or DC voltage control via chopper duty ratio controlling. If you are using back-to-back hard switching inverter, then you can have MPPT or vector control of both converters. That means vector control can be used. If you are using back-to-back hard switching inverter with the reduced switches, then you can use a generator control MPPT inverter current control or through the PI controller. So this is with the PMSG based grid interfaced wind energy conversion system. You can use these many control scheme depending upon which kind of converter you are using, whether rotor side or the grid side. Similarly, if you are using a DFIG from kilowatt to megawatt capacity, then if you are using diode bridge or SCR inverter, then sliding mode control can be used. If you are using SCR based rectifier and inverter both, then dual thyristor firing control you can use. If back-to-back hard switching, then you can use vector control on or the space vector modulation of or the PWM for MPPT maximum power point tracking. If you are using a matrix converter, then you can use a vector control on rotor and the supply side using double space vector PWM switching. And the last is if you are using induction generator in the kilowatt and megawatt range, then you can use vector control or you can use the fuzzy logic controller and also use the slot harmonics or the model reference adaptive system. So there are n number of control techniques are being used these days. You can use whether fuzzy logic, you can use the digital control, you can use the analog control, you can use DTC, vector control, anything can be used depending upon the requirement of what you are requiring and which kind of a generator you are using. Now looking to this is covering all the, you can say, generator, induction generator, which is asynchronous induction generator, then permanent PMSG, then your DFIG. There is another scheme which is called isolated topology where transformer will be used. So in this isolated topology, I'll be covering, I think I have around next 15 minutes, I may be able to finish up 15-20 minutes. So the other in this, I'll be discussing about the introduction. What are the different configuration? Mostly two configuration: fixed speed and variable speed wind turbines. Then control algorithm. There are so many control algorithm. I can give you an overview of many control algorithm. And then the most important maximum power point tracking. And then one of the experimental results I will also be showing here. So if you see the classify, we have a fixed speed induction, your isolated wind and VEX system. So there are two types of this. One is isolated asynchronous generator. The other one is PMSG. In variable speed, we have doubly fed induction generator, EMSG, and isolated asynchronous generator. These are the three options are available. And mostly we have a variable speed because wind speed, we do not have a control. So if you talk about the off-grid, well, small turbines, 50 watt to 10 kilowatt, you can use. Battery charging, you can use. For water pumping also, you can use during the off-grid. An isolated grid, you can use the turbine of 10 to 200 kilowatt, which can reduce generation cost in remote areas where you can use a wind diesel as a hybrid system. And it can also high to low penetration you can use depending upon the availability of the wind. These are the few examples of isolated grid wind energy system. The two photographs, one is installation of 50 kilowatt turbine in West Bengal. The other one is a 50 watt kilo turbine in Canada. So this is where wind turbines reduces the consumption of the diesel fuel. So that's why it has been used, and it is more reliable, and the maintenance are also very, very low. So it's a very cost effective solution. If you see another off-grid wind energy system, well, there are again installation of 40 telecommunication tower in Arizona state, then power for a remote village in Brazil, then hybrid wind energy system in Chile. So this is again, you can say there are many countries are using the off-grid wind energy conversion system, maybe sometime hybrid with combination with the fossil fuel and wind, both are there, and sometimes they are, if the wind penetration are fair enough, then they are using only the wind energy system. So as we know that we have fixed speed prime mover operation and the variable speed. These are the two options are available in case of the wind energy conversion system. So what are the challenges associated in autonomous wind energy conversion system? We have to control voltage, frequency, which because grid connected system, these two are the important parameter: voltage control and the frequency control. Because as the speed is changing of the wind, the frequency and voltage both will change. So your controller should ensure whenever you are injecting power to the grid, it should have maintained constant voltage and constant frequency. You can also harnessing the optimum power. That means you can extract the as maximum power as possible. But yes, as per the bed's limit, you cannot go beyond 60% of the ideal power. You can go for a load balancing also. You can go for a neutral current compensation also, load leveling in all the three phases, and also ensure the power quality issues. So yes, all these issues can be tackled by wind energy conversion by selecting a proper control technique and proper objective function. So this can be done and this can be achieved as per your requirement and as per your whatever you are objective you are fulfilling. So this is the for fixed speed. There are three options are available: isolated asynchronous generator based wind energy conversion system, PEMSG based, and doubly fed induction generator based. These advantage already I have told you that it is simple and low cost, low maintenance, but then poor power factor, power fluctuation, and then the mechanical stress on the turbine. So this is one of the topology you can see. Here you have connected excitation capacitor, then you can connect the voltage source converter here, and then it is a battery energy storage. So this is a battery model is being connected where resistance and capacitor in parallel and resistance and battery in series. So overall, this is a battery energy battery model which is charging the battery basically. Now, if you see some other reported topology where you can say this is your wind turbine, this is asynchronous generator, then this is excitation capacitor bank, then balancer and balanced load is being connected here. Then you have a three-leg VSC, and this is again BESS means battery energy storage system. Then you have a star delta tertiary winding. So once we are talking isolated transformer is integral part, which is creating isolation. So voltage is being injected using the, you can say, turns ratio being maintained here. So this is a tertiary dummy, you can say delta connected three-phase winding is being connected. Star connected is also there in both sides. So this is star delta tertiary winding transformer configuration. So voltage is being injected according to the requirement on the load requirement and the compensation, the reactive power compensation requirement. Similarly, you have transformer in all the three, you can say, phases, and depending upon the N1 N2 turns ratio you can inject, and then you can, if you are charging the battery, you can charge, power flow will be on this side. If you are making a reactive power compensation from this side, power will feed back to this side. So it is a both side power flow can take in place. So I'm just showing you the different kind of options are available for your isolated asynchronous generator based wind energy conversion system. So here system becomes more and more complex because transformer is also there and you need to inject depending upon the turns ratio. This is also another topology where you can say T connected transformer is being connected here for sorry, for ensuring the power quality as well as the charging of the battery. This is another topology where you are zigzag transformer. This transformer is known as the zigzag transformer, which is being connected on the load side, and according to the requirement, the purpose will be done whether charging the battery, where feeding, or whether compensating the reactive power requirement of the load. These all have been reported in the paper. Then you have a star delta transformer. On the primary side, if you see, it is a star transformer. On the secondary side, it is delta transformer. So again, all these your IGBTs need to be given the PWM pulses. So all control algorithm has to be done. So whenever transformer will be there, it will be a star, you can say, your isolated topology would be there. This is another reduced switch. So here the midpoint capacitor to capacitor has been connected from the center point. The connection has been done through the inductor of the star connected secondary side, and here zigzag transformer. So in this case, we have reduced the switches. So once you reduce the switches, obviously cost will reduce. So this is another, you can say, isolated topology. This is another topology where hexagon transformer is star in the primary side, that means on the your turbine side, and on the converter side, that is battery side, you have the hexagon. 6 windings are there which are displaced by certain angles. So that is 60 degree each, 360 divided by 6. So this is hexagon transformer. This is again a zigzag transformer to be connected with the VSC. This is the control algorithm. Now All the earlier topologies I show you, the using the different transformer, whether it's a zigzag transformer or whether it's a star or delta transformer or hexagon transformer. Now for all this, you have voltage VF control, voltage and frequency control scheme should be used for the current compensation. So this is how the controlling, you have to sense the voltage, and according to that you have to generate a reference current, take the actual current and then compare it, and then pass through the PWM generator, that is a sawtooth waveform comparing the error. And once you are controlling the frequency, then you have a PLL. From that you convert, take the frequency, compare the frequency, and through frequency PI controller you are giving the frequency. So that means you have to control both voltage as well as the frequency in this case. So this is the control scheme for the same. This is using the PI controller, another control scheme. This is called I cos phi based voltage frequency control. So again, you can use the I cos phi, that means the two component of the current, I cos phi and I sin phi. You can sorry, you can use that control as well. This is the SRF based voltage frequency control. So that means I'm just making you aware that there are so many control schemes are available. If you make a little change in the control scheme or reducing the one of the leg, your one paper, if you're able to simulate it, one paper is ready. And for first time, if you are running the simulation, it will really give you a pain in terms of understanding the control algorithm. But yes, the moment you can able to run the first simulation, it would not be too tough to run other scheme, because other control schemes are very close to each other. Certain parameters are changing. Basic root cause is you have to generate a reference current, sense the actual current, compare them, pass through the PWM, that is sawtooth waveform, the error, and then it will automatically generate the PWM, 3 PWM pulses, because for 3-phase there will be a 3 current, and then you connect the NOT gate for complementary, you can say, pulses for the remaining 3. This is a power balance theory based VFC control scheme. Again, due to the I think time limitation, I may not able to go much detail into it. Similarly, it is instantaneous symmetrical component theory based VFC control algorithm. This is again to be, most of the cases it is PI controller, because steady state error in case of PI controller will be 0, and your filters will be used, and then you can compare voltage and current, and then ultimately you are generating the current references. Then this is the parallel operated asynchronous generator. If you operate 2 in parallel, that can also be done. You can operate 2 in parallel. Then this is another scheme of static compensator, using the static compensator, that voltage and frequency control. This is with PMSG. Earlier one was with your induction generator. The same thing can be done with permanent magnet synchronous generator as well. So here, this is a zigzag transformer, and this is a voltage frequency controller, which is the control scheme can take care of the PWM pulses as per voltage frequency control. This is the block diagram for generating the voltage frequency control. Now these are the results which can dynamic performance of wind energy converter system for balanced as well as the unbalanced linear load with fixed wind speed. So here you can inject the load, you can reject the load, and still you can ensure while zooming your current, you can see that they are perfect sinusoidal, maintaining good power quality at the input side. Similarly, this is for again for a non-linear load, earlier one for the linear load. So your load side current will be non-linear because load is non-linear, but then input side, we should not pollute the source mostly. So source should be at the source side, your current should be perfect sinusoidal. Voltage would automatically will be there, but we need to ensure the current should remain the sinusoidal. Whenever you are injecting the load, whenever you are taking off the load, in any of the case, it should be maintained and stabilize the DC link voltage. This is the result again taken at 8 meter per second for the linear load of 27 kilowatt, where generated power is 21.5 kilowatt and 7.5 kilowatt. So this is also the load. You can see whenever the load is being injected on any particular line, it is completely 0. But then there is hardly any impact on your input side current waveform. It is perfectly sinusoidal. So if one of the phase, suppose load is reduced to 0, is still input side current has been maintain perfect sinusoidal. This is at 9 meter per second for the non-linear load. The compensating current, the third current is compensating current, that will be very much distorted because compensation has to be done in accordance with the load requirement. But your 3-phase current, which is being drawn from your grid side should be maintained sinusoidal, and that is what objective is. Your load side current, as you can see, this load is changing. Load side current is very peaky current. It is like your square kind of a current is coming. So that is not of our interest, because load is non-linear. That will certainly draw non-linear current. This is again varying from 6 to 7 and 7 to 5. That means increasing and decreasing. Your speed is still perfectly, it is being maintained. As you can see, second graph, you can say their magnitude is keep on changing, but their shape is perfectly maintained, which ensures the power quality is being maintained throughout. Now coming to the last one, which is DFIG. You can have now in DFIG, you can say that there will be a isolated topology. So delta and star transformer is there, and then you have a battery is also there, and then you have a rotor side converter, a stator side converter. So rotor side converter is injecting into the rotor side, and then stator side converter would be requiring the battery charging, or it is feeding back to the load. So depending upon the power flow, because in DFIG power can flow in either direction. That's the advantage of DFIG topology. So this is one of the variable speed wind energy conversion system with DFIG. So this is what the advantage that you can, with DFIG, you can always achieve a constant frequency operation. You can converter power rating is always reduced because it is working at a self frequency. Operation below and above synchronous speed is possible. You can have control of both active and reactive power, and power factor of stator side can be controlled by controlling rotor current. So rotor current, what you are injecting, you can control automatically. The power factor will be maintained at the stator side. This is again for maximum power point tracking. There are 2 or 3 important parameters. That is, CP is the power coefficient. Whenever you have to achieve a maximum power, CP max, you have to maintain this tip speed ratio at a nominal range. And beta is basically a blade pitch angle, which is required to control. If wind speed is too high, you change the blade pitch angle, it can control the wind power or wind flow, so that it will not damage your the blade of the wind turbine. Also, the power should not be very much excessive. So if you have to control the power, you keep on changing the pitch angle of the blade. But yes, if you have to extract the maximum power, then CP max, that is power coefficient, should be maintained at a your nominal tip speed ratio. Then with the DFIG, the main advantage that, as I said, you can achieve 4 coordinate operation, mode 1, 2, 3, 4. If sub-synchronous speed, you can achieve motoring mode as well as the generating mode, and super synchronous speed, you can also achieve motoring mode and the generating mode. But this is only possible because you can have a bidirectional power flow. So you can have motor, you can have generator operation, anything you can achieve. These are the few other schemes are available. So I am just skipping these things because these are the other control schemes. I am just now showing you some hardware. These are the results with the DFIG at a difference speed, that is 6.1 meter per second for the balance and unbalance. Again, you can see for rotor side these currents, and for your stator side these currents are perfect sinusoidal, where you are injecting the load or rejecting the load. You see the variation in the current of all the 3 phases, LA, LB, and LC. It is changing, and compensating current is also keep on changing. But your this rotor side and the stator side, it is completely maintained your current as sinusoidal at a different speed and different, you can say this is at 8.73 meter per second. Again, it is completely, you can say it is a non-linear current due to non-linear nature of the load for all the 3 phases, and the loads are also not balanced. Still, your currents are being maintained completely sinusoidal at all the 3 phases. This is what the speciality of the DFIG. Similarly, this is at 10.7 meter per second. It is also being maintained. Suddenly load has been rejected, increased, so the current at all the 3 phases has been reduced, but nature of the current, shape of the current is being maintained, which ensures for all the 3 phases on both the side, which ensures that power quality has been maintained, and wind speed also is being maintained constant. So this is what the simulation results. Now I'll be just showing you few of the experimental result. This is from the fluke power analyzer. This is the steady state performance of the DFIG based wind energy conversion system at 8.4 meter per second speed with a rotor speed of 1380 rpm. Now you can see the current THD. This is the voltage THD. Voltage THD will always be lesser, but as per the IEEE standard, you have to maintain lower THD, less than 5% for all the three phases. So this is for phase A, phase B, phase C. You can see that THD is 4.8%, 4%, and 4.6%. So this is from the fluke power analyzer. These results has been taken, and as you can see, your sinusoidal voltage and sinusoidal current has been maintained throughout. So this is how you can able, and this is also showing you that how much active and reactive power is being there, and your DPF here is 1. Similarly, at a different speed, that is 9.15 meter per second, rotor speed of 1500 rpm, is still more is the speed, better would be the result. So here you have 3.6, 3.3, and 3.2. THD is well below 5%, so it is fulfilling IEEE standard. And then one is for super synchronous speed, which is 1670 rpm or 10.2 meter per second. Your THD is further being controlled at current THD 2.9, 2.4, and 2.3. So it's very much acceptable, as you can see, as far as your implementation is concerned. Once you implement it in the hardware, this is what dynamic performance we also need to check. Suddenly you are increasing the load and suddenly you are removing the load, whether your current and the speed and your power is being stabilized or not. So this is how you need to check, and the result has been taken from the I think Tektronix power analyzer. These results has been taken. So as you can see, whenever we are injecting the load, rejecting, small changes is happen, but again after that it will stabilize. So small change will happen, but after that it will stabilize to the same voltage and same. So whenever change has occurred, that change will be reflected in the waveform, but then the controller has to work immediately in the small time, and then it will stabilize again. So this is how, again, if you make the changes, suddenly change will occur, but again it will stabilize. And how fast it will stabilize, that is decided by your controller. So once you are suddenly rejecting the load or suddenly injecting the load, that dynamic performance will ensure that how fast your controller is controlling that particular change and accommodating it. So with this, I will just come to the end of the presentation. That I just would like to conclude that classification and design of various topologies of three-phase configurations for wind energy conversion system have been investigated for feeding wind power into the grid and simultaneously ensuring the power quality improvement. So, well, these days, power quality at the input side should be maintained. We should not pollute the supply. That is the most important thing. Whenever we are generating the power, it should be maintained. Although all kind of loads in electrical are non-linear in nature, so load side current will be always peaky current will be drawn. It will have a square shape, triangular shape, but then input side, the source side, your current should be perfect sinusoidal. That is what we require. The performance of various two-stage system configuration with different control strategy have been implemented and evaluated on MATLAB platform, and then hardware as well as shown you. All topologies with induction generator, permanent magnet synchronous generator, doubly fed induction generator had been extensively simulated with various control scheme, and performance have been compared with focus on better result ensuring MPPT. So it is again most focus was on assuring the MPPT. Different isolated topologies using transformer of wax have also been explored through the simulation, and results have been compared using various control technique with different objectives. Although hardware result I have not covered up here for the isolated topology, it has been confirmed that DFIG outperforms in terms of better power quality performance in comparison to other reported topologies with improved overall efficiency and reduced cost for a specific application. So DFIG has taken a lead as compared to other two, that is whether it is a fixed speed or variable speed. DFIG cost wise, performance wise, efficiency was, DFIG is better as compared to the other two. These are the few references while preparing the slides have been used. So with this, I'll come to the end of my presentation. If there would be any queries, I would be happy to answer the queries.
Participants, any questions? Okay, sir. Then thank you, sir, for your valuable insights and informative talk on wind energy conversion system, current trends and challenges. Thank you, sir, and participants for joining this session. Thank you all.
Thank you very much.
Yes, sir.
May I leave now?
Yes, sir. Yes, sir.
Okay, thank you very much.
Thank you, sir.
I just show you my first slide. I have a mail ID as well. If maybe it is very exhaustive present, I have covered many topologies. So if anyone has any query who is doing research or otherwise exploring wind energy conversion system, then you can mail me any of your queries. I would happy to answer your queries.
Dear participants, you can note down the email IDs, sir's email ID, and share if any doubt is there. Okay, dear participants, you can leave now. The session is over.
Thank you.
Thank you, sir.
Thank you.